Hi, welcome to Digital Electronics. I'm talking on chapter number 4, Function of Combinational Logic Circuit, under the subtopic of 4-bit parallel binary look-ahead carry adder circuit and also BCD adder circuit. So I will cover two subtopics today. So the first one, the 4.3, 4-bit parallel binary look-ahead carry adder circuit. So look ahead is the important words over here. So 4-bit look ahead. So this method was used to eliminate relative slow rippling effect of carry bits of the carry adder. So in a circuit, when you have lots of bits to process, you need to wait one by one. So let's say half full adder, the first full adder will work and then it will come out with the sum and the carry. This particular carry will be used in a second full adder, and then later on it will process, it will come out with another result. It will give of carry. This carry will be input of the third full adder. So the sum and the carry cannot be produced until the output occurs. This will cause delay. Higher number of bits will cause longer time to wait until it works. So for this, we come up with another idea of look ahead carry adder. So first we come up with the result, then we do correction later. How we do this is usually the look ahead carry produce relatively earlier output carry at each stage by processing using carry generation and carry propagation. The carry generation, you need to assume the input is A equals to B, which is 1. So that's why the carry generation CG is equals to A dot B. While for the carry propagation, you need to assume the input A or B equals to 1 and C out is 1. So that's why you have CP equals to A plus B. So both of these, you're going to have an output carry at each of the full adder by the formula of CG is the A dot B plus CP, which is the A plus B, and the C in. So how we going to see how we're going to use this in our circuit. So let's say you have a stage 1, at the very stage 1, you're going to have a A1, B1, the input is C in 1. This is going to process, you're going to have the sum and you have the C out. This particular C out is the response. To have a look ahead, you're going to have C out is equal to C in dot CP1 plus CG1. So this is how you're going to use at this particular stage. And then the response for the C out 2, you're going to have C in 2 dot CP2. C in 2 is your C out of this one. This formula is the response of C in 2 dot CP2 plus CG2. For the C out 3 is equals to C in 3 dot CP3 plus CG3, and CP4 equals to C in 4 dot CP4 plus CG4. So this is how you're going to prove it in a circuit. So from the C out from the circuit 1, full adder 1, you're going to have CG1 plus CP1 dot C in 1. So you're going to put is as C in 2 because it is equal to C out 1. So you're going to put over here, then you're going to expand and you're going to obtain a circuit equation as this one. This one you're going to put as C in 3 in the full adder 3, and you're going to expand, you got this information, and this particular information you're going to do with the C in 4, which going to have out this one. So in overall circuit, you will do a correction of like this. So you're going to have a, so this is similar to this stage, but you're going to have a small modification in this part. So you're going to have the Cin is normal, A1 is normal, B1 is normal. You have the sum 1, but you're going to have a circuit, extra circuit of Cg1, so which is this part. You're going to have a Cp1, which is this part. So this is the formula that you used before. You're going to apply again over here, and then C in 2, which is equals to your C out 1. So you're going to have a result over here. So you do this one by using this method. When you tap the results over here, you're going to have a faster results, and you're going to have looking ahead results of here C4, C3, C2, and C1. Next, going to talk about the BCD adder circuit under the 4.4. So for the BCD adder, adder perform additional between two BCD numbers that takes to consideration on the value whenever it is accessed by 9 by doing some correction of adding 6. So how are we going to do this is to understand why the BCD adder is invalid. So there is an illegal code in the BCD, which is 1010, 1011, 1100, 1101, 11110, and 1111, which stand for number 10, 11, 12, 13, 14, 15. Why you use this? In your average 7 segment, it only appears 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The next after 9, it should go to 0 back. So that's why we shouldn't have 10, except for the hexa. But this, we are talking about 7 segment, is going to be only 9. And also, when you have a value exceed of 4 bits, then we need to know this is already excess the maximum value of more than 9. So how, this is the strategy we're going to use. We have to use 2 unit of 74LS238, 238, which is a 4-bit parallel adder. We need to use a checker whether the result is not more than 9 by looking at C out, S4, S3, and S2. So if you see, this is the formula. So we want to check. So for the decimal, number 8 is 1000, decimal 9 is 1001, and decimal 10 is 1010, as been mentioned earlier. If you see over here, your S is 1, 1. Before 8 is going to be 0, 0, 0, 1, 1, 1 is number 7. So whenever S4 is become 1, so this is activated. But the S3 and S2 and S1 is 0. For the number 9, the S1 become 1. Because since it becomes 0, 1, and 0 again, so the S1 cannot be used as a result. But the thing that is uniform over here is 0, S3 is 0, 0, S2 is 0, 0, and suddenly for the decimal 10, S2 become 1. So for this particular reason, we're going to use the C4 result, which is we want to make sure it is not more than 15. So whenever this axis of 15, so it become C1, C4 will become true. So we don't want that one, so it should be 0. And then we're going to have no to the S4. S4 is 1. So it's make sure F4 is always 1. And S3 and S2. So in this case, for the decimal 10, when S2 and S3, 0 plus 1, you're going to have 1. And then 1 times with S4, which is 1. 1 times 1, you're going to have 1. And since the C4 is 0, is okay. But this become x become 1 in total. If x is true, and when the bit then we need to add number 6. Otherwise, if x is, let's say we see the decimal 9, s2 is 0, s3 is 0, 0 plus 0 is 0, s4 is 1, so 0 times 1 is 0, and c4 is 0, so 0 plus 0 is 0. So for that, we don't have any action to proceed. Let's see at the circuit. So this is how, when you cascade two 4-bit adder circuit, so you're going to have a small modification. Okay, your C in is going to be C out is this particular C in is going to be grounded. This C4 is going connected to a circuit. This circuit is going to be your correction circuit. You have an input over here, A1, A2, A3, and A4. B1, B2, B3, B4. This is your BCD adder, second BCD adder to add. And whenever you add both of A1, A and B, the value, whenever it is less than 9, your sum will go directly over here, and you don't need to add anything before you get this one. But if the value is more than 9, let's say 10, so when there is an indication of 10, so this value will go over here, this value also going over here. This particular circuit will process, add 6 to here. So 10 over here will add another 6 over here. 10 add 6, it will become 16. 16 is technically, for the first LSB, it become 10000, 4 zeros. So because of the first carry is 1, so you're going to carry over here, your sum will be resected to 0000. So for example here, this is more clearer. So your sum will go over here, and lastly over here. If the C4 is when the value is excess by 10, excess by more than 9, 6 will be added by using this method, and will go over here. So how you're going to have 6 is, you're going to connect the the VCC to the pin number 2 and pin number 15, which responds in a form of 0100. So you have 0110, which is decimal 16, sorry, decimal 6. This will be adding to your sum, and the output will become reset to 0, and your C4 will become 1, which is not going to be used in this particular circuit. Now you can continue to the document 4.5 for decoder and encoder. Thank you.